This is section 4.6 on isosceles and equilateral triangles. First off, we have a couple of new reasons for proof. The first one is the isosceles triangle theorem, which isn't the definition of an isosceles triangle, which only says that two or more sides are equal to each other. Instead, the theorem says that if you have an isosceles triangle, then the opposite base angles must be equal to each other as well. So if these two sides are equal to each other, that means these two angles have to be equal to each other. Whereas the converse of that, our isosceles triangle converse, says that if you have two base angles that are equal to each other, it means then that the opposite sides are equal to each other. Not a definition, but we have a theorem and we have a converse that are both true. And then we have this equilateral triangle corollary. A corollary is kind of like a piggyback off of a theorem. Because that theorem is true, that means that this corollary is an implication of that. In other words, if all three of these sides are equal to each other, that means all three of those angles would have to be equal to each other by using that theorem and transitive property. Likewise, if these three angles are equal to each other, we could use the isosceles triangle converse to get all three of the sides equal to each other, as well as with the transitive. So we have this equilateral triangle corollary. Let's see what those theorems do for us as we look to solve problems. First problem we have says that triangle VSY is isosceles, and it looks like VS is equal to VY. It says the perimeter is less than 45. Which side of this triangle is the base? Now the two legs are the two sides that are equal to each other. The base is the one that isn't necessarily equal to them. So I'm going to assume that 2x minus 8 is the base and check to see if I set these two legs, or that I think are legs, equal to each other, I get x equals 3. Well, if I plug x equals 3 and I get lengths of 10, 10, and negative 2 for this bottom length, which means, in fact, 2x minus 8 couldn't be the base. These two sides of 10 and x plus 7 could not be equal to each other, so that's not the base. And then I'll try another side. Let's say x plus 7 is the base. That means that 10 and 2x minus 8 would be the legs equal to each other. So if I set them equal to each other and solve for x, I get x equals 9. Plugging that in makes this side equal to 10. Makes this side equal to 16. 10 plus 10 plus 16 is less than the perimeter of 45. It means that segment VY must be that base. Next problem. We have two isosceles triangles. First one here on the right, we have the angle of 55 degrees, which means that the other two angles would have to add up to 125 degrees. Take 180 minus that to get these two angles. So this 2y plus 64 will set equal to 62.5 to get y equals negative 3/4. And then going into this other triangle, which is not congruent to the first one, but it still is isosceles, we know that these two angles are going to be equal to each other. And with the exterior angle theorem, these two angles together have to sum to 62.5. Divide by 2, they both then are going to be equal to 31.25. We'll set this expression equal to 31.25, and it turns out x equals 55. And now with proof. Here's our given and what we're trying to prove. I'd encourage you to pause the video and try to work it out on your own first. If you're stuck or if you want some help, you can go back and watch this video. But I'll start off by saying that we have the given, and then this step saver reason, the isosceles triangle theorem, is going to be very helpful in this one. First of all, we're going to convert the definition, using the definition of congruent segments, to say that CA is equal to CE. And because those are equal, then we can say that this base angle of CAE equals that base angle of CEA. There's our first step. Using the angle addition postulate in transitive, 1 plus 3 equals this, 2 plus 4 equals that. Transitive, we can then get 1 plus 3 equals 2 plus 4. We already had 1 equal to 2, so if we subtract 1 off of the left, 2 off of the right, we get 3 equals 4. And then converting that, we get angle 3 is congruent to angle 4. Next one is another one I'd encourage you to try on your own first. You can follow along with what my proof is here once you've tried it on your own. I'm going to convert to equal rather than congruent early on in this proof. Since measure of 1 equals measure of 2, I'm going to use the isosceles triangle converse to get AT equal to BT. And we already had AT equal to AE, so through a transitive, we can say AE equals BT, and then use the definition of congruent segments to conclude. I didn't ever actually use this angle bisector, so I could have done it another way, but it was something I didn't have to have. And here is the last proof. We have the given. Right away, I'm going to use the isosceles triangle theorem to get these base angles equal to each other. And what I notice then is that I almost have this yellow triangle congruent to this overlapping green triangle. If we say symmetric BG equals GB, that gives us enough to use side angle side to prove the green triangle congruent to the yellow one. With corresponding parts of congruent triangles congruent, we have segment IB is congruent to segment RG, and then at the end we're going to convert to get